What if I was figuring out not just how far to walk around the perimeter here, but let's say that this was something that I wanted to paint. Let's say I wanted to paint this. If I painted the whole circle, I would know what the area is, right? What's the area of a full circle? The area of a circle is pi r squared. But what if I just want to paint that orange part and I want to know what the area is? I would have to subtract out the pi wedge, right? But how would I find the area of the pi wedge? It's almost a triangle. Well, we're going to derive that formula. I'm going to show you how we can derive the formula. Here's what we want. If I have this right here, I have this right here, and this is angle theta, and this is S, okay? This is called a sector of a circle. Bless you. It's a pi piece. So it's not considered a triangle because it has the curved edge. It's like a pie piece or a pizza pie, right? Pizza slice. Pie piece, pizza slice, whatever helps you think about it. Pizza slice. And we're going to derive how to find the area of that. And the reason we can do this is because it's nothing more than a proportion. It's a proportion of the whole thing. So let's go ahead and do for one whole rotation. For one whole rotation all the way around. We know the area is pi r squared, and we know the angle theta is 2 pi. All right. And then for the sector, the area is A. We don't know what it is. We're just going to call it A. We don't know what it is. But we do know that the angle is what? It's theta. So I think we can do parts to whole. So using a proportion, we could say the part, which is the area of the sector that we want, is to the angle theta as the area of the whole thing, which is pi r squared, is proportional to the full angle, which is 2 pi. Okay, that's how we did the proportion. And when I set up a proportion, I always like to start with what it is I'm looking for in the top. Now, all I got to do is solve for A. So if I solve for A, I notice here that the pi's divide out, and I multiply by theta, and I have it divided by 2. So this is a 1/2 r squared times theta. And there it is. There's the formula now. Instead of setting up a proportion every time, there's the formula for the area of a sector of a circle. It's 1/2 r squared times theta. Notice there's no pi in there. No pi in there. And divide it out, right? 1/2 r squared theta, 1/2 r squared theta, 1/2 r squared theta, 1/2 r squared theta. Let's go ahead and put it in a box. If theta is the central angle in the circle, where theta is measured in radians, then what's the area of the circle? It's given by 1/2 r squared theta. Okay, so if I were to come back up here, let's say 300 degrees was 5 pi thirds. So here we go. The area of, I'll use orange here. The area of this sector is 1/2 r squared theta. This is r, this is theta. What's the radius? It's 5 miles. And what's the angle theta in radians? 5 pi thirds. So now if you simplify that, 5 squared is 25, times 5 is 125 pi, and then the bottom you're going to get 2 times 3, which is 6. And then what would the units be if this is now miles squared times radians? What's miles squared times radians? It's miles. Yeah. That gives you the area. Like if we're still talking about the city, that would give you the square um, footage, if you will, but it's in miles squared. Square miles. They usually measure city by square miles. So this would give you the number of square miles the city is in that little orange area. Now let's do it down here as well. Mr. Kilford just scarfed down a piece of Freudian pizza, okay, that had a central angle of 40 degrees. And I know that because he always measures them for me. So what's a Freudian pizza? A Freudian pizza is a pizza with little slices of Freud on it. And if you look carefully at the Freud picture, you can decide whether that's blood on his face or marinara sauce. Okay, I'll let you decide. But that's a Freudian slice of pizza. The central angle we said was 40. So this here is 40. 40 degrees, 40 degrees. If the slice came from a 14-inch diameter, so if it's a 14-inch diameter, the radius is what? 7 inches. Good. Part A, find the perimeter of the slice that he just ate. I'll ask you for a question similar to this when we quiz over this. Find the perimeter of the slice. Well, the perimeter of the slice, if you want to start here, okay, you're going to walk down here 7 inches, right? Plus you're going to walk down here 7 more inches, yes? And then you're going to walk along the crust, which is the arc length S. So the perimeter should be 7 plus 7 plus S. When I simplify that, I get the perimeter is 14 plus, and what is S? What's another name for S? It's R theta, right? S is R theta. So if we substitute in now, we get 14 plus the radius is 7, that's inches, times theta, which was 40 degrees. So is that last piece going to be 280? No, that's degrees, and we need to convert it to radians. So if you didn't do it off to the side, you can convert it right here in this problem. You could multiply by pi over 180, and you'll see that the degrubbles divide out. And now we have inches times radians, which is inches. So there's your exact answer, and if you want to know what it is, you can type that in now. 14 plus 7 times 40 times, we'll multiply pi in here because it's not an angle, it's a length divided by 180. So this is 18.886. And what would the units be? Inches, right? This is inches, and that's inches times radians, which is inches. Yeah. Pi also has no units. Okay, so that's cool. That's taking the arc length and then using it in combination with the radius twice to find perimeter. Cool. Part B, determine the square footage that he consumed. The square footage. So if you just think about across the face of it right here, like the square footage of toppings, that would be the area. So the area, of course, is what? What's the formula? I won't give it to you. If it's in a box in this section, you need to know it. 1/2 r squared times theta. 1/2 r squared times theta. 1/2 r squared theta. No pi. 1/2 r squared theta. Let's see if I know all of these. This is going to be 1/2. The radius is 7 squared, so that's 7 inches squared, times theta, which is what? Well, let's convert it off to the side. 40 times pi over 180. We did it over here in the calculations, but let's see if we can simplify without a calculator. 4, it goes into itself twice, 9. So 2 pi ninths. This whole stuff is 2 pi ninths. So I'm going to just plug it in as 2 pi ninths over here. And that's rads. And now notice the units are going to be what? Well, I have inches squared right here. See that? So inches squared is going to be square inches, and then times radians should still be square inches. But that's an exact answer. We'll go ahead and type this in. That's 49 divided by 2 times 2 pi divided by 9. That area ends up being 17.104 inches squared. Now, is that the true measure of how much pizza that you eat? The square footage of the topping? No, you usually count by slices, right? Like I had 15 slices or something like that. But really, if you want to talk about how much pizza you're physically ingesting, it's not linear, right? It's not squared, it's cubic. What do we measure in cubic units? Volume, right? Density volume, not like loudness volume, of course. So that's what we want to know. So if this pizza slice is, let's go ahead and for the simplicity's sake, let's just say that it's 1/2 inch thick. 1/2 inch thick. How can we figure out the volume of a slice? Well, volume is just multiplying by the third dimension. So here we go. The volume is going to be nothing more than the area of the face times the thickness, which I'll call, what would I call it? X? We'll call it X. This is kind of like a sector prism. It's not a rectangular prism, but you have the shape on the top and the shape on the bottom, and it's the distance between them. So it's the area of the face, which we just found, times the thickness. So the volume is going to be 17.104, which is still in your calculator with all of the decimals. And then you're just going to multiply by 1/2 or divide it by 2. And the volume ends up being 4.5 cubic inches of food. And that's one slice. Now, is he full after that? I don't know. Let's see. Hey Siri, how many cubic inches does the average stomach hold?
Okay, I found this on the web for how many cubic inches does the average stomach hold. Check it out.
1 liter of food. Okay, Siri, what is 1 liter in cubic inches?
Here's an answer from AskNumbers.com. 1
Okay.
liter, L, is equal to 61.0237441 cubic inches.
Okay. So look, if our goal is to fill up that stomach, we're at a pizza buffet, right? Fill up that stomach. If the average stomach can hold that many cubic inches, and one of them is 4.5, how many can we eat? Well, let's see, 61.023 divided by 4.5. We can eat 13 slices. Wow, before we fill up our stomach's average capacity. That sounds like a challenge to me, or permission, right? Now, most people stop short of 13 slices because they're not, what's the word I'm looking for? Pigs, right? Right? You can feel full before your stomach is maxed out capacity. So anyway, 13 slices. Good to know. All right. So as many years as I've done this problem, I've never gone this far and figured out how many slices. I never asked Siri what the average stomach capacity is. So now we know. All right. Wasn't that fun? Very good. All right. Most of you have seen this thing before, maybe not with so many sub-partitions, but this is called a compass rose. A compass rose. And it's how Boy Scouts and aviators and people that are lost with a compass, how they navigate. Okay? We got due north, of course, due south, east, and west. And it's kind of like a coordinate plane, isn't it? Because between east and north and west and south, south and east, it's 90 degrees. Okay? But if you're going to go halfway between east and north, you're going to go at the 45-degree angle, right? This is a 45-degree angle. We don't say 45 degrees. You would tell someone, I traveled northeast, right? Well, it starts getting a little bit interesting because if you were then to take the halfway point between north and northeast, you would get north northeast, north northeast. How many of y'all have ever used that as a direction? Oh, I headed north northeast, right? North? Did you stutter there? No, no, no. It's north of northeast. That's kind of what that means. North of northeast. Now, if you wanted to split that in half and travel on this direction, you would be traveling NBE, which B is short for what? What word? It's short for a 2-letter word. by. North by east. North by east. Okay? Uh-huh. Do we have a south by southwest? No, that's not on here. South by southwest. That would be like in between here, south by west and south southwest. So when you're talking about general direction, oh, we're heading north. That's good. Maybe northeast, the 45s. But after that, it gets kind of cumbersome and tedious to reference your direction in this manner. Now, how many degrees are in between consecutive little rose points here, compass points? If this was 45, this was 45. Half of that is what? Half of 40. What's half of 45? 22.5. And then half of that, what's half of 22.5? 11.25. And that's the magical number. Because now, as you rotate and you pass through each of these compass rose points, you're traveling another 11.25 degrees. Okay? So let's go ahead and come over here and figure out what we're looking at here. Example 5. There's other ways to navigate from due north. And I mentioned it here. If you've ever heard of a heading or a bearing, they're kind of the same thing. Headings would be like I'm flying on a heading of east by north, okay? Or they could say I'm on a heading 11.25 east of north instead of north by east. So headings and bearings start from due north just like the compass rose. Let's go ahead and figure out example 5. Find the angle measure for the following. Southwest. If we're traveling southwest, we're on a bearing of southwest, we're traveling on a heading of southwest, that's going to be on what angle? Southwest. First of all, we got to find southwest. Right here it is. Southwest Airlines. They're still sitting in the plane gate, right? Now, if we were on the coordinate plane, which we're not really, we're on a separate compass rose, but if we were on a coordinate plane, it would run through here and through here. Now, we always start from the positive x-axis and rotate upwards, right? That's for us. But when you're talking about navigation, navigation always starts due north. It always starts due north, and it rotates that direction, counterclockwise, or clockwise, I should say. Now, it's still 360 degrees all the way around, but we're starting at a different place, and we're rotating in a different direction. So I just want you to be aware that different orientations on the same thing for different reasons, okay? This is in a different field of study. It's not coordinate geometry. But that helps us figure out the angles, because southwest now, how far is it? I know southwest is going to be, I'll draw it here. Southwest is going to be at least 180, right? And then plus what? Plus 45, yeah. So what's 180 plus 45? 225 degrees. So if you told someone that you were traveling on a heading of 225 degrees, they'd be like, oh, you're traveling southwest. And you're like, no, I'm traveling delta. And they're like, no, the direction southwest, silly goose. They're the same. 225 degrees from due north in the clockwise direction. All right, north-northwest. North-northwest. Let's see. We got to find north-northwest. North-northwest. Okay, that's over here. So there's a couple of ways to do this one. You could say, normally I'm going to travel all the way around to here, which is 270, plus how much? How many of these little tick marks do I travel past? 1, 2, 3, 4, 5, 6, right? There's 6 of them. So it should be this. It should be 270 plus 6 of, how many did we say each of those were? 11.25. Okay, and if you type that in, 270 plus 6 times 11.25, you get 337.5 degrees. And how far is that from 360? Well, that's 22.5 degrees off. It's 2 clicks. So you might hear people say they're traveling on a heading of 337.5 degrees, or you might hear them say they're traveling on a heading of 22.5 degrees west of north. West of north means start here and go this way. I've heard that before. Now, the whole purpose is to try to clearly communicate what you're doing and where you are. So west of north works for pilots, but I want you to list it in terms of 337. Okay, y'all go ahead and do CB by yourself. CB, southeast by east. Yeah. So CB is down there in the bottom right. So from due north, you know you're going 90 full degrees to get to due east, plus 1, 2, 3 rose points, and that's going to be, so 3 times 11.25. You type it in, you get 123.75. So again, if you're on a bearing, ships usually do bearings, planes usually do headings, but it's really the same thing. Courses, I've also heard them called courses. Like I'm traveling on a course of 123.75. So a lot of different lingo in the industry. But for us, it's 123.75. Okay. All right. So I can give you some of those compass rose points and have you convert them in the future. But just another application of angles. All right. Here's one last thing that we need to cover in this comprehensive, awesome section. Often, situation in which we measure angles, we have angles that change. Okay, so we started talking about distances back in the day, right? This is so many feet long. But when you start talking about how fast those distances change, like things moving, you're talking about velocities. So stagnant quantities are fun to work with, but in the real world, most things change. And that's really what calculus is about. It's the study of change. Well, if we measure how fast these things change with respect to time, that's how we can get velocity. Now, linear velocity would be distance over time. Linear velocity would be distance over time. But we have this new thing called angular velocity, which is how fast the angle changes or how fast something is spinning. Okay? So let's go ahead and define it. The angular velocity, which we use omega, it's not a W, it's not a W, it's omega. Okay, so it has little curly Q's on the end. Looks more like this. Omega. The angular velocity of a point moving in a circular path is given per unit of time by this. Omega is theta over time. Omega is theta over time. So it's the angle divided by time. What would some of the units of this be? Let's look at the example of units. What could we have? Well, what are some ways we can measure rotation? Theta. We have radians, don't we? So we can have radians per, and then time we can have like minutes. Radians per minutes. Or what's another way to measure theta? How about degrees? We can have degrees per hour or something like that. Or we can have rotations. Rotations per second. Those are all units of angular velocity. It's a measure of angle, which we've measured in radians, degrees, and rotations, divided by any unit of time. Okay? Now, if we have an object that's moving along a circular path instead of a straight line path, we can actually figure out its linear velocity along that curved path. Right? Have you ever ridden a merry-go-round? Or have you heard of a merry-go-round? Or you ridden a ride that spins? You're traveling through a large distance if you're way out from the center because the circumference is larger, but that thing is rotating at one rate, and you actually feel velocity along a curved path, and it makes you feel like you're going to fly out, right? Well, linear velocity, remember, linear velocity v is just distance over time. It's just distance over time. This is your rate, distance equals rate times time. Right? Distance equals rate times time, divide through by t, and you get d over t equals r, and r is equal to v. Okay, so that's where it comes from. Well, if our distance is being tracked around a curve, then our distance is going to be what? What do we call the distance around a curved path? It's part of the circumference. It's called the what? Arc length s, right? For spinning, the velocity is the distance s divided by time. Now, what is another name for s? Do we have a formula for s? R theta. So we get r theta over t. And now look at this. I can associate this with what? What is theta over t? When you measure how fast something spins with relation to time, you get its angular velocity, right? Which we just said was omega. We defined it to be omega. And there you go. We have now derived the formula for the linear velocity of an object. In fact, it's just r omega. It's directly proportional to the radius. Directly proportional to the radius. Okay? So we need to know what's going on up here. But really we need to memorize this formula. V equals r omega. Let's look at this. Y'all are looking at the clock in here sometimes, right? How are we doing on time? Okay, let's see if we can get example 6. Determine the angular velocity in radians per second and the linear velocity in inches per second of the second hand of a clock that's 5 inches long. So if you want to draw a clock, here's the second hand. It's 5 inches long. Now, first of all, let's figure out the angular velocity. The angular velocity says radians per second. Angular velocity, omega, is just theta over time. So, do we know what that is? Well, let's think about this. We measure angular velocity in like RPMs. Y'all have the tachometer in your car, revolutions per minute. That is a type of angular velocity. So this thing makes one rotation every how far? This is its angular velocity. The second hand makes one rotation every what? 60 seconds. Okay. Now it says radians per second, so I can change that. What is one rotation in radians? 2 pi. So you can either say 2 pi over 60 seconds, or you can come up here and convert it. One rotation is 2 pi radians. But do I have radians per second now as my answer, as my units? I do. So this simplifies down to pi 30ths radians per second. That's how fast that little thing is spinning. And now if I want to figure out what the angular velocity is, right out here, If I was like sitting on the tip of this little second hand, it was going around, how fast would I be going if it was a ride? Well, that's the linear velocity, and it's r omega. So I can just plug in now. That's 5 inches times omega, which is pi 30ths radians per second. And what would the units be here, first of all? What's inches times radians per second? Inches per second. Cool, because radians are unitless. They're just a placeholder. 5/30ths, that's pi 6. So I get pi 6 inches per second. And if you want to know how fast that is, we can actually type that in. Pi divided by 6 is 0.523. So if you were sitting on the end of the second hand, you would be going, whee! You'd be traveling a half inch every second. All right, good stuff. We'll pick up there tomorrow. More applications, more angular velocity.